Okay, got it. Gotta get YouTube going. I guess put this in there. Not public, private, unlisted. There we go. Now we got it. Man. Till you get the negative one next pay period. You guys know on Jeopardy that if you finish with negative, you have to actually pay them that money. Know that? No. I don't really know. That would really suck though. I really went for it. Negative 12,000. It's true. It's true. Survivor, you have to sacrifice most of your self-respect for going on Survivor. binge Survivor. There's what, 30 years of episodes at this point, something like that. How many seasons of Survivor are there? Unbelievable. Expert survival people right there. People you definitely, all that really teaches you, right, is that you don't want to be on an island with those people. That would finally give them something to do. Let's see. Two minutes. All right, it's 12:30. Let's get rolling. Lord, thank you for bringing us together this afternoon. Thank you for everything that you do for us and all the blessings that you've given us. You are an awesome God, and you're there for us. You are a provider, pray that you would continue to help us throughout this semester, that you would just give us the things that we need to be successful. In your name we pray. Amen. All right. We're going to talk about a bunch of stuff. We're going to recap. We're going to recap sources of error again, for reasons, and then we're going to jump into topic 3. We are cruising through this stuff, guys. So we're going to hit topic 3. We're going to start talking about how do we actually measure stuff. We've talked a lot about the theory behind measurement, right? We've talked about it abstractly, but how do we physically create something to measure a quantity? And that's what topic 3 is going to be talking about, right? Yet another perfect class. Nobody confused about anything. Fantastic. Feeling strong, right? We're feeling strong. Just in case, what did we actually talk about last week? What did we cover? Yeah, Isaac. We did do those things. We did oscilloscope awareness training, right? And so now everybody feels super comfortable with knowing how to read the oscilloscope, right? And if you don't worry. We'll have plenty of opportunities this week to read some more stuff off the oscilloscope. And use the function generators and all those things. And by the time we finish the class, you'll all feel really great about it, just in time for the summer to roll along, and then you will just forget it. Ohm's law, huh? All right. Well, Ohm's law is the Hooke's law of the electrical world. Okay, that's what it is. It is a linear equation that gives us the amount of current that we get through a resistor, or we can use it to find voltage drops, right? Or you can use voltage and current to find how big of a resistor you should have, right? Yeah. Fantastic. Great. Right, there it is. Nailed it. Here we go. Here's the things that are due. The things with the line through it are already due. They're gone. Can't do those things anymore. I am grading those homeworks. Posted solutions. If you guys didn't see them, please go look at the solutions. Right? They are up there. Hey, Kenny.
Yeah, my bad.
Hey, Ken. Anyway. Here's the deal. I'm grading them. They'll probably be graded by next class. Okay. Then I will hand them back to you, but you already have the solutions. So, that's nice too. So you can look at those. Homework 2 is going to be due this week on Thursday, right? So I would highly recommend doing those 3. I know it's a big ask to ask you to do 3 questions. I know it's rough times. But please. And then, if you wanted to start homework 3, you could do that too, right? Because that one's gonna be due a week from the next time. And then we've got this measurement and data ethics paper that's due on Super Bowl Sunday, right? Where it will likely be, I was really hoping for Cowboys Bills, but it's not on the menu anymore. That's too bad. I really wanted to relive the glory days of my youth, right? Anywho, I would recommend, we'll talk about that next week. When we get a little bit closer, we'll go over the rubric. We'll talk about metrics for success in the ethics paper and all that. And then we've got our first exam on the 9th, right? So we'll go through some of that later, but let's just recap sources of error. This is one of the things that we talked about during last week on Thursday, right? We introduced it on Tuesday. We kind of tied it up, but just to recap it one more time, right? We want to understand sources of error because we need to know we want to know what's messing up our measurements, right? Now, it might shock you to hear this, but in the real world, nothing works the way that you want it to. Full stop. And if you didn't take thermodynamics, I'm sorry, I spoiled the point of the entire class for you. Okay. Ecclesiastes, the class, right? Meaningless, meaningless. Everything is meaningless because the second law, and you cannot has efficiency higher than 40%. My bad. Okay. But what actual things contribute to possible errors that you are getting in your test setups? That's super important. Why? Because that's what you're getting paid for as an engineer. As an engineer, you're getting paid to say, there's a problem with this. I know where the problem is and I can fix it. That is where the bucks are. Anybody can run a test, right? Not everybody can troubleshoot a test. We want to be able to troubleshoot and provide solutions, right? That is what engineers do. We solve problems. So what is a calibration? It's a relationship between an input and an output variable. Some people call these transfer functions. You'll have a whole class where we talk about transfer functions when you're seniors, right? Unless you already took it, in which case you probably, that was the best class that you had in all 4 years. I know for a fact, it's the best. Calibration does not eliminate system errors. It allows us to quantify the uncertainty in a piece of equipment. So we talked a lot about how do we calculate uncertainties. Most of the time, those are things that we get from spec sheets, right? We have 3 sources of calibration error, right? We talked about this: standard or reference values, instrument or system under calibration, and the calibration process itself. This is curve fitting, right? But also remember, there are slight variations in the way that you run tests. They might not be major, but you can't with 100% accuracy reproduce everything that you do every time, right? You can try, right? But turns out that it's very difficult, right? So we try to get the best. The reason that we run multiple tests, right, is so that statistically we can say that we have a good idea of where our values should align, right? Now, if you haven't taken statistics, right, some people say, well, mechanical engineers and BSEs and whatever you happen to be don't need statistics, and that is false. It's very false, right? Statistics is really important. And if you ever get into Six Sigma training and getting your green belt or your black belt, that is all statistical analysis of manufacturing methods, right? You will have a certain number of parts that are scrap. You want to minimize that. Why? Because if you have less scrap, then you have more things that are good. You can sell things that are good. You can't sell things that are scrap. Remember, you can't spell scrap without crap. Okay. Errors that arise during the can't read the top there. We can certainly fix that, right? Data acquisition errors are errors that arise during the act of acquiring data. Include things like senior or instrument errors. Pretty sure that's supposed to say sensor, not senior. Or instrument errors, even typos. Those can be a sort of data acquisition error. Right, you didn't write down the data correctly, and so you had a typo. All right, not accounted for in calibration and uncontrolled variables, things like measurement system operating conditions, right? So these are like extraneous variables, right? So if you are measuring something and the atmospheric pressure changes from day to day, right? If you're measuring temperature, you'll get a slightly different boiling point of water, right? That would be a measurement system operating condition. Sensor transducer sage, right? You have some transducer error that is there, right? Some signal conditioning error. We talked about this, right? This is like when you filter your data. If you filter data, you're losing data points, right? You smooth data, you're losing data points. Your output stage error, right? Process operating conditions, sensor installation, environmental effects, spatial variation effects, temporal variation effects. Okay, if you're near a black hole, you will get different data than if you're not near a black hole. Okay. Great. Yeah. If you're operating your system near a wormhole, right? That's where one end was even. Anyway, never mind. We're not going to. If you're interested in the physics of time travel, Neil deGrasse Tyson has a really nice podcast where he interviews Charles Liu about the physics of time travel, which is interesting, but not really applicable in any real life scenario. Well, anyway, so there you go. So we can have error from just acquiring data, right? Okay. And then there's data reduction error. So by manipulating the data, we put error into it. Curve fit, truncation, and modeling error. When you make a mathematical model, you make some assumptions, right? That reduces the order of complexity of your model, but it also adds error into your model because it is not 100% correct, right? And I'm going to say something, and you guys can take this as you like, but anybody who's trying to find a unifying theory of everything is foolish, because that's a really great scientific pursuit, but will not help you in your day-to-day life at all. But you know what does help you? Distance is equal to rate times time, which is a really simplified mathematical model for how far you get to go based on a velocity and the amount of time that you're going. All right. Anyway, systematic versus random error, right? We didn't really talk too much about this. There's some big statistical things here, right? There's little b and big B, and we can talk about that in a second. Systematic error remains constant in repeated measurements under operating conditions, right? So this is like a bias in your data, right? This would be like a bias in your data. You can talk about the systematic standard uncertainty at two different confidence intervals, which are the capital P's. There's a 68% and the 95%. We talked a little bit about this in passing. Most of the things that we are going to be worried about are 95% confidence. The confidence interval tells you that 95% of the time you will return the correct answer. 5% of the time you won't. Okay, that's what it's telling you. So that's clearly better than 68% because 32% of the time I'm not getting the correct result, which you got to start somewhere, though, I guess. Correction. If you know the value of your systematic error, then you can account for it, right? And so you can, all of the scales that all of the digital scales that you've ever used have a tare function, right? Why? Well, because of this. Because there's some amount of system error. Why? Because it turns out that the plate that you're measuring the thing on actually weighs something, and it's sitting on top of the sensor, and that's a systematic error. So if we want to get the actual weight of the thing that we are measuring, we need to tare the scale, right? T-A-R-E, not T-E-A-R. Okay. Important designation there. It's like brake and brake, right? Like a brake for your car, or you're braking the car, right? Funny story. When I was a sophomore in college, we had a mini dragster project where we had to make mini dragster race cars, right? And I was in charge of the braking system. And I would intentionally spell it the wrong way to freak people out. Like, we are braking the car. EA, not AK, right? Anyway, random error. When we repeat measurements under fixed conditions, we also get random errors that appear as scatter. So we can talk about the standard uncertainty, which is S sub X bar, which is the standard deviation of my distribution divided by the square root of the number of trials that I did, right? So it's a sort of average. The random uncertainty given confidence interval can be found in table 4.4 in your book. It's a statistical measure, right? And so if you took stats, there's lots of table lookups in stats, right? You go to the table, you find your values, right? So this is a systematic error because I have a tight grouping that is consistently some distance away from the bullseye, assuming that I'm aiming for the bullseye, right? Which is not necessarily the best throw. It depends on the game that you're playing, right? Trip 20s, typically what you want. Depends on the game you're playing. This is an example of random error because these points happen seemingly at random. So if you were to throw the darts with your eyes closed, you would have some random error, right? And if you were to take a half a step to the left, you would have a systematic error, right? That's the basic difference. Darts are used a lot in probability, right? Also, urns with balls inside for reasons I'm not really sure about, but it's class. You know, I've got this urn with 6 green balls and 4 red balls in it. What are the chances that I can select a green ball without anyway. Do a participation thing. So what I want you guys to do is rip a page out of your notebook. I'm going to collect this and put your name on the top. I'm not grading this for correctness. I'm grading this for process. So work on it, right? You're gonna get 20 minutes and you're gonna do the following thing. We have a tachometer. I had a very Russian professor in college who would pronounce it tachometer, right? So, we have a tachometer that has an analog display dial graduated in 5 RPM increments. The user manual states an accuracy of 1% of the reading. We want to estimate the design stage uncertainty in the reading at 50, 500, and 5,000 RPM. When you're done, right, we will go over it when you're done, but I'm going to collect them at some point after you finish, okay? So you got 20 minutes. Begin. Commence. Start. No. Exactly, exactly. I know. Gotta work on that. I think it's much more creepy if I whistle while you guys are doing the activities, and then when you're watching the videos back, then you just have this whistling. It's like not even like a tune, just like random, like it sounds like wind is blowing past your window. Yeah. Start. Maybe let's see if the Doppler shift works. You guys tell me. You guys tell me if that was Doppler shifted. Appreciate it. Meow.
Only done the first two, green.
What's up, Isaiah? I mean, you can message it to me on Halo.
Okay.
That's easy. Awesome.
Like that's not fun. Maybe.
Looks good.
But that's sad. I guess I'll put on. Yeah, so you can right over here, your hands like. I would get that this. Yeah. I mentioned the file. Well, I put.
Yes, good. You guys good? Any questions? You guys good? Any questions? You guys got any questions? Good. Alright. Nice.
So, on the homework, so if this is 6.02, uncertainty be half of 0.02, or because it's in hundreds place, 5,000 or uncertainty. Kind of the same.
Yes. So how big, if you were to write the whole number out, right? So if you were to write the whole number out and use the last digit, right? Like what would it be?
You're supposed to use like that digit, or say you have 100 and would it be that 5 divided by 2, or would it be 1? I don't know.
So would this be 10,000?
Essentially, yeah. Right, because it's given as times 10 to the 6, you can do it how you thought, right? Yeah. Divide by 2.
So it's not like there's
Right. Because in this sense, you're given,
If it was just 6.02 by itself,
right,
it would be 0.01 would be our uncertainty.
yes. It's because of the way that it's reported, right? Think of it as sig figs. Yeah. It's a figs thing, right?
If it told us it was measuring in 0.01 or whatever, then our uncertainty would be.
So in this case, right, the other way to think about it is, well, let's think about it this way too, right? Because of how it's given in that sense, right? There's two different ways. You can say you cut that in half, right? The last digit in half, or you can say, well, I might be able to eyeball 0.00 5, right? Because it's halfway between the 10 or the thousands place, and right. So you'd be like plus or minus 0.0, plus or minus 0.005 times 10 to the 6, right? Because in this case, you could probably make a reasonable guess at what this is as long as it's halfway between either, right? But so there's two ways you can think about it. But remember, certainty, what we're actually doing are trying what our plus or minus is, right? So this is the plus or minus whatever this happens to be. And so with resolution, it's typically important to know, it's typically important to know resolution, but if you just have a digital readout, you just take the least significant. Right? 2 minutes. Is there any questions, comments, concerns? I always really concerned. I get really nervous to ask that last one. Oh. No, you guys are good. Good. All right. Fantastic. You guys doing all right? I'm fine. Yeah.
Yeah, we're doing good.
Questions? All right. Seems like everybody's done. So talk about it. I'm going to ask you a loaded question. Well, it's not really a loaded question. I'm just going to ask you guys a question. Do your results make sense?
Yes.
Why?
Because as we go higher, that's
Okay. Let's talk about this, right? What's driving your uncertainty of this measurement device? It does depend. All right, what does it depend on, Alex? Yeah. Depends on the RPM. At low RPM, what's driving your uncertainty? The resolution, the zero order uncertainty. When we have a small RPM, the resolution matters, right? At low RPMs, what happens as we increase our speed? Right, we have now exceeded. Who cares if at 500 you're off by 5? Right? Nobody cares. Who cares at 5,000? Well, I care even less. What about at 500,000? You're not going to notice anything, right? So everybody hopefully got the fact that U sub 0 is going to be the same, regardless of what the reading is, right? The key thing to cue off of here, well, it helps if I have the pen on, right? Is that we need half of the resolution for U0 or U0. So that means that U0 will be constant for all measurements at half of 5 RPM or 2.5 RPM. Okay, and this is constant no matter what we are doing. What does change is the accuracy uncertainty, because we are told that it's 1% of the reading, right? Anytime that you see that phrase of the reading, make sure that you are applying that uncertainty to a specific reading, typically a nominal value or some value that you're interested in measuring, right? Some true value. So at 50 RPM, right, the low end, we get a UA of 0.01 times my reading, right? And I'll write it like this for longhand right now, right? Which is just 0.01 times 50, which is 0.5 RPM. And if I want my design stage uncertainty, it's UA squared plus U0 squared square root. So 0.5 squared plus 2.5 squared. 2.5 squared is significantly larger than 0.5 squared. So without me doing any actual math, I would estimate that I would have an expected uncertainty here of around 2.5, right? Because 2.5 is so much larger than 0.5 when we square it. If we square a fraction, right, and here's where squares get crazy. If I square a fraction, I actually get a smaller number by squaring it, right? Because this becomes a quarter when I square it. So I have decreased the uncertainty by squaring it, which is a weird thing to think about, but it's what happened, right? And what did I do with 2.5? Well, I increased 2.5, right? But what ends up happening is I get roughly 2.5 RPM, roughly. Now, some of you will be like, well, actually, Dr. D, you will get 2.56, which does not round 2.5. That's true. It does not. So either way. And so we can call it 2.6 if you really want RPM. And you'll often see this as plus or minus 2.6 RPM, right? You'll roughly see it as 2.6 RPM, plus or minus. The plus or minus is important because what the uncertainty is telling us is that there is some range of values that we can expect this to fall in, right? Remember, the measurement is going to be, so let's put it this way. At 50, if you're actually reading 50, your actual measurement could be, what, 52.6, or it could be 47.4, okay? It's going to fall somewhere in that range reliably. And you're like, well, that's not that bad, right? Because that seems pretty small, right? So, but what happens when we increase this to 500 RPM, right? So UA is now 0.01 times 500 or 5, right? Yeah, 5 RPM. And so UD is the square root of 2.5 squared plus 5 squared. In this case, we can't really discount this. We're going to assume that we'll probably be somewhere around 5, right? We end up getting plus or minus 5.6 RPM. So at 500, we could be reading 505.6 or 496.4, right? Somewhere in that range. That's what this is telling us. Again, I mean, it's roughly 1%, right? It's a little bit over 1% of the actual reading, which makes sense because we added something to that 1% error, right? Now, to bring it home, let's do this. And this means that UA is 0.01 times 5,000. So we end up with 50 RPM as our uncertainty. And if we did our design stage uncertainty, now 50 is so much larger than 2.5. We're going to expect an uncertainty around 50. And what we get is plus or minus 50.1 RPM. And so at 5,000, right, we're at 4, we'll just call it 50, right? Because I'm not going to do that. We're either at 50 or 5,050 RPM or 4,950 RPM, which at those speeds, losing 1% is probably not that big of a deal, right? At that speed. All right. So that's kind of the process, right? Now, there's some more complex versions of this problem that you'll probably see in the homework, right? But this is the general cadence whenever we're asked to find uncertainties, right? Determine what you have, apply those errors, determine the uncertainties, then you'll probably have to find a design stage. Remember, you can do design stage for multiple parts of a sensor, right? You can have a sensor design stage uncertainty, and you can have a transducer design stage uncertainty, and then you can add those together by taking the square root of the sum of the squares of those things, right? And so it's essentially find the uncertainty, square root some squares, square root some squares, right? It's like if you're not doing the square root of the sum of the squares at some point during these problems, you're probably doing them wrong. Just throw that one out there.
Earlier we had talked about how the
Yes.
It could be if the square root sum of errors like this, the research, the linearity of the that's the same thing as the accuracy.
So those are different. We're using the same variable in different ways. So the book has that nice variable U sub A that they use for things. What you'll see that I tend to do is I tend to make for each part that I have, right? And so I will calculate like the hysteresis uncertainty on its own. I'll calculate all the uncertainties apart, and then I'll add them together at the end, right?
But theoretically, right, we got U sub A, that's equal to the square root sum of them different.
Potentially. If you're given an actual uncertainty error in a spec sheet and a hysteresis error, you can't assume that they are already combined. Good question. Any other questions? No?
And then in that case, you combine the uncertainty or and the hysteresis and all that.
Yep.
Okay.
Then that just all rolls into your design stage, right?
Yeah.
Yeah. There you go. All right. Let's start topic 3. Topic 3 is analog device. This is where like we're actually going to talk about how to make things, right? Cool. That's cool. People like to make things, right? We want to, by the time we're done with this, our objectives are to construct current and voltage sensing circuits, to construct Wheatstone bridge circuits for resistance bridges, to evaluate the performance of amplifier circuits, evaluate the performance of signal filtering circuits, and determine the sample rates of digital data acquisition using engineering methods. Okay. And we're going to do this all under the guise of analog devices, right? And from the first homework, I know we didn't talk about it, right? But an analog signal is a continuous signal and a discrete signal is a digital signal, right? And the difference, we'll talk about the difference in a little bit, right? But today we're going to focus on current measurement, voltage measurement, and then everybody's favorite, the voltage divider circuit, right? Because I told you, we're going to live in the voltage divider world for a bit. We're also going to make lots of Wheatstone bridge circuits by the end of the semester. So, everybody loves those. They're the best. All right. So I want to measure current. Okay. I want to measure the current through a wire. And you guys all took physics 122, right? Which is everybody's favorite physics class because it's all about electricity and magnetism and how to do blood sacrifices and all those things that, anyway, a DC electrical current can be measured using principles from electromagnetism. Now, turns out that if I have a wire, right? I have a wire. Imagine for a second I have a wire and I am going to pass a current through that wire because it seems like a good idea, right? And it's going to be going in this wire here. It's going from from left to right. And I put that wire in a magnetic field, right? What happens? Well, it creates another perpendicular force because it creates its own magnetic field, right? Surrounding the wire by just passing the current through it. And by doing that, these two magnetic fields will interact and we can cause some motion through that, right? So analog device that responds to the force exerted on a current carrying wire. So typically what we do is we take not just one wire, but a whole mess of wires, or I guess technically it's one wire. You're just going to wrap it around a thing a bunch of times. What's that thing? It's typically some sort of magnetic piece of metal, like iron, right? And we wrap this iron with a coil of wire, right? And if we do this and we put current through it, we induce a larger magnetic field because by having all of these overlapping magnetic fields, right, which travel around this coil in this way, and if they travel around in this way, right, we can use the right-hand rule and we can see that our magnetic field should be pointing perpendicular to the board, right? Because the wire is circular and we will have a radial field surrounding it. And if you put this other magnetic field perpendicular to that, then you have a really nice interaction, right? Or we can either attract or repel the other magnetic field. More importantly, this presence of this other magnetic field is going to cause this to turn if this is pinned in the center, which it is. And how do you know that? Because there's that X in the middle there. That's how you know that. And I just told you. All right. So in this case, right? In this case, if we have these two interacting fields, we get this force couple, right? Because we have a north side and a south side, and that other magnetic field is constant, and it forces us to rotate, right? With the force couple, which provides the torque here, T sub mu, right? This is the basic idea around how motors work, right? This is the basic idea around how motors and other actuators like them work, is that we're having these two magnetic fields that interact with one another, right? And that's what we want. So the flow of current can be measured by a pointer, right? So if I attach a pointer, that red thing isn't there for reference of coordinates. It's actually an indicator, right? So if I want to know how much current is flowing through this, right, I can calibrate this motion to point to a certain amount of current. And this is the basics of how an ammeter works, right? Oh, an old school ammeter, right? Because now you have the digital one, you just put the thing in line with your circuit and it just tells you, right? Well, so there's there. But if we were interested in determining how much torque we were going to get, this is how we would determine the torque. The torque, T sub mu, right? And this is the torque generated by the magnetic field that is just us taking these force couples and determining how they cause rotation, right? Is capital N, which is the number of turns of wire that you have, right? The number of wraps that you made, times I, which is the current, times A, times B. B is the field strength. A is the cross-sectional area of the wire. Times sine of alpha, right? So you need to know what angle you've rotated through. Why is it the sine of alpha? Well, remember that this force is going to create a torque, but if we call this the x direction, right? Let's do this. I call this the x direction and this the y direction, right? This can be broken into two components. Let's use a different color. Here's my force. This force travels through the center, which is where we are looking about the point of rotation. So it does not contribute a torque, right? So the torque only is this component, only is enabled from this component of the force. This angle between here and here is alpha, right? Well, I guess that's not alpha, sorry. No. Anyway, that's a different angle. Alpha is the other one because we're using the sine of that. And if you use the sine of that angle, you're getting the wrong thing. So this sine depends on us knowing the angle between here and here. That angle. Well, sorry, here and here. All right. Yeah, either. A should be the cross-sectional area of the wire itself. Okay. So there's a couple of things in here that you're not going to be able to change if you have one of these devices shelf, right? You're not going to change B. You're not going to change A. Well, I mean, you could, but why are you going to rewrap all the new wires? And you're not going to change N. So if you were to buy an ammeter off the shelf, those are things that you can't change. But what you can change is I, which is what we want to measure anyway, right? So, all right, so it's good. We know this torque now, right? Here, there's the things. These are the things over here. Got it right, nailed it. Cross-sectional area of the current loop, which is the wire, right? The cross-sectional area of the wire. Magnetic field strength, the current, the angle between the normal cross-sectional area of the current and the loop, and the number of coils. All right, so if I wanted more torque, there are certain things we can do, right? You can replace the magnetic piece that's producing your magnetic field with something that's stronger, right? That would increase the amount of torque, get you more motion. You could increase the number of turns of wire, right? Which we've already said, right? We're assuming we're building one of these, right? And so that's what we're looking at, right? We control that in some way. Right? We can adjust I, but since we want to measure I, we're probably not going to mess with I, right? And you can use a larger gauge wire, right? You can do all those things. What this creates is something called a D'Arsonval movement. Okay. It's a magnet and a coil assembly with a pointer. And again, these same principles get exploited for us to make motors, to make linear actuators. We'll talk a little bit about that later in the semester, right? Current flow through the coil results in a corresponding rotation of the pointer. A spring is employed to restore the position to zero, right? So the spring is really important. If the spring's not in there, you are going to set this, and when you turn it off, it won't go back to zero. So it will always be offset from the time that you use it the first time, unless you're able to go in and set it back to zero, right? So turn spring is really important. right? An ammeter is a current sensing device that operates with a Darson-Wall movement. So here's another picture of something that would a little bit more realistic than the PowerPoint image that we made using shapes, right? So this sits inside of some magnetic field. We've got a north side and a south side to our field, right? This is on an axle, right, with a rotational spring sitting at the top. This is just a hunk of iron, typically, that we have wrapped with coils of wire, right? And then as we apply current through here, these two magnetic fields interact, either sending it in one direction or the other. And when we turn it off, the spring brings it back to zero, right? That's it. Pretty simple. It's a pretty simple device, right? But it uses dark magic to operate. Your car's fuel gauge, modern car fuel gauges work in this way, right? So, and notice I said a modern car fuel gauge. When I say modern, I mean probably 1990s or better, right? Before 1990, you might have a float gauge in there, and a float gauge is really accurate as long as you're not, going uphill or downhill. Okay. Anyway, so what happens in here, right? I've got some sensor in here. This is a float gauge, right? Well, this will work for what we're trying to do. Modern sensors do not use a float gauge. I can't emphasize this enough. Okay, if you've ever driven an older vehicle uphill or downhill, you know that you can falsely modify the amount of gas that you have in your tank. All right. So I also want to say this: just because your gauge says that it's full, doesn't actually change how much gas is in there. Okay, by going uphill or downhill. Just throw that out there. Anyway. Okay, so in this case, let's imagine that this is an electric sensor instead, right? And so what happens is this creates some electrical signal that goes through this wire up here, comes around to our fuel gauge, and the fuel gauge has its own little Darson-Wall movement meter in there, right? And you can see it kind of down here behind this portion. There's a little magnet in there, right? That portion is actually the return spring sitting on top. It's a torsional return spring, right? It will, if you might have noticed that when you turn your car off, it goes back to empty. That doesn't mean that every time you turn your car off, there's magically no gas in it. That's not what that means. Yeah, I know, it's crazy. Where does it go? Anyway, so that's the general idea of how. Most of the dials and gauges on your car dashboard work in the same way. Now you're like, well, I have a fancy car that doesn't use, what am I? Yeah, that's digital. There you go. Fancy car that's digital, right? And so that's great. That's a different thing altogether, right? But we're not talking about that. We're talking about specifically this for a fuel gauge. The fuel gauges still to this day work in this way, right? Still on any car. I challenge, well, I'm not going to challenge. There are cars that I recognize that there are cars that use different things, but the majority of dashboards do have some Darson-Wall components on them, right? Yeah, maybe not, who knows? What else is a Darson-Wall movement, right? Well, we're going to watch this video. It's going to say the same things that I just said, but you're going to believe it because it's on YouTube.
So we just finished talking about how you might get a torque
on a coil that has a current going through it. If I have a coil here with a current going through it, and I put this in a magnetic field, depending on the orientation of the coil, if I set it up just right, I can get a torque on that coil and cause it to rotate. I guess if the current's going this way, it'll rotate this way, maybe. And if the current's going the other way, it'll probably rotate the other direction. Okay, cool. And here's a practical application of that. Now we can measure currents. And I guess we can measure voltages as well. I want you to look in here. This is the workings of this volt ammeter. It's very nice, built with wood cabinetry. Oh, probably almost 100 years old at this point. But I want you to look inside here. You've got a coil this direction, and you've got a magnet there and a magnet there that's creating a magnetic field, probably pointing either this direction or that direction. I don't even know, but it is either left or right. There's also a spring right here. And so we've got green wire and black magnets on the side, a needle coming off of this coil. And if I cause this coil to feel a torque, the coil will go, like it's in this orientation right here, it will go whoop, like that, and that will show that there is either some voltage or some current, depending on the way that I've got these knobs hooked up. So I draw a little sketch right here, and I want to point out to you, here's what I want to say. I've got this sketch with the green wire, and I didn't show the spring yet because I thought it would get cluttered, but there's a coil spring on here. The coil spring prefers to be in a certain orientation. It's probably ultimately hooked onto the needle and hooked onto something else, and it prefers to be right there. But if there's a torque on it, then it will move, I guess storing some energy in the spring, to right there, and then if the torque is gone, I guess the torque will be gone if I don't have a current going through the green wires. If the torque is gone, then it'll just go back to where it was. So that resets resets the ammeter and voltmeter. And also, there's probably a little adjustment on these guys down here. There's probably a little screw adjustment, or I can turn it to change the natural orientation of that needle. So that's pretty cool too. So how could I make this be a more sensitive galvanometer or ammeter, a very sensitive ammeter? Let's look at what that torque is made of. Torque is N times I times A times B times the sine of theta. So I could either have more loops of wire, and you notice those wires were thin. There are a lot of loops of wire right there. So I could increase that. I could increase the current. Well, that's just the meter doing its job. So that doesn't mean that I'd have a more sensitive meter. I'm getting more torque as I'm getting more and more and more current. Let's make this a magnetic field pointing that direction for the sake of argument. And then I could also increase the area inside. So the bigger my loops are, if I expanded those loops, I would make a more sensitive galvanometer. So if this were a smaller galvanometer, it wouldn't be quite as sensitive. I could also make a stronger magnetic field outside. And you can bet that in 1915 or something, when they made that, they were probably using the best magnet technology available. Now we would probably make them with some neodymium stuff and make it quite a bit stronger magnetic field. So all of those things are good. The one more thing that I could do that is independent of torque is I could make a longer needle. And there are some beautiful machines that were made a long time ago with that, and I'll show you one of them now. Bye-bye. And finally, proof positive that I work in the best high school in the United States of America. You can talk all you want about fancy teachers, new additions to the building, but I present to you Big Bertha, the most beautiful galvanometer you have ever seen. Not only that, she's a lecture table DC galvanovolt ammeter. That's right. She can take care of any problem you got. Look at all those connections. See that? Look up there in the works. You can see it all right in front of you. You get a current running through that wire right there, through any of these contacts right here. That will create a, force on those charges, and that needle will move. Look how long that needle is. Whoa! If that gets a tiny, tiny little torque on that coil in there, that needle will move a tiny bit, but you'll be able to see it because it's such a long needle. Check out the backside right here. She's got all those connections, so you can change the range. Look at the directions there. That's right, made in the United States of America and printed in metal. Big Bertha is the best galvanometer that you'll ever see.
Sure. Sure. Yes, sir. All right. So that's how we measure current, right? We're exploiting that torque equation. We're measuring current, right? So how do I then get a voltage? Run it through a resistor in Ohm's law. That can't be possible. Somebody was confused about Ohm's law at the beginning of class. Unbelievable. How are we? Can it? 100%. You run it through a resistor, and you know what that resistance is, and you now know what the current is, right? And so you can find the voltage drop, which is the voltage, right? So it turns out you put the Darson voltmeter in series with the resistor. How does it work? We just told you how it works. The Ohm's law thing, right? There it is. Beautiful Ohm's law. Many exclamation points. Examples of these meters. Here's an example. That's, an ammeter. I know it's an ammeter because it's measuring microamps. That's very small amps. 10 to the minus 6. Oh, look at all of these. We were talking about these before. It might be because I took these slides from Professor Bullock, so it's likely a Corvette.
I can also see the Corvette logo.
Turns out that you can literally use it in any car you want. It just doesn't anyway. All right. This shows you your engine temperature, right? This is your oil pressure, your tachometer, tachometer, your speedometer, right? How much battery life you have. Oh my goodness. Your fuel level. All really important information. All right there. All Darson voltmeters. All of them. All right. We're gonna watch another video, because I'm phoning it in today. There you go.
Let's say you had a circuit here and you had a battery with a voltage V, and there were resistors 1, resistor 2, and resistor 3 up here, and there's current flowing through here. What if you wanted to experimentally measure the voltage across some of these elements? You'd have to use a voltmeter. Voltmeter looks like this. So a circle with a V in it is the symbol we use for a voltmeter. How do you use it? You take that voltmeter, you bring it over to here. I can't plug it in the circuit like that. What I do is I take the leads of the voltmeter and I just connect them to either side of the circuit element that I want to determine the voltage across. So if I do this and I connect those leads right here, this voltmeter will tell me the voltage across R3. Or take the voltmeter, put it over here, and if I connect the leads across R1 in parallel, notice I'm hooking up the voltmeter in parallel. Voltmeters you always hook up in parallel. This now will tell me the voltage across R1, and if I wanted to make sure my battery was functioning correctly, I could take my voltmeter and I could hook up the leads across the positive and negative terminals of the battery and see if the voltage across the battery is what I think it is. That's how you use a voltmeter, always hooked up in parallel. But if I wanted to measure the current, I don't use a voltmeter, I use an ammeter. And for an ammeter, you do not hook up an ammeter in parallel with the element you're trying to measure. You'll probably blow out the ammeter. I've done it a few times. It's embarrassing. Don't hook up the ammeter in parallel. I'll tell you why in a minute. But what you have to do is hook it up in series. So if I wanted to know the current going through R3, I could just stick this ammeter right in here. One lead would plug into one side of the ammeter. The other lead would plug into the other side. This current would have to flow straight through the ammeter. And this is telling me how much current goes through R3. It doesn't matter which side I put it on. The current going into R3 will equal the current going out. So you can put it over here too. But it's got to be hooked up in series. So you have to disconnect. It's kind of a pain to hook up an ammeter sometimes. You have to disconnect something here, then connect that connection to the one side of the ammeter, connect to the other side of the ammeter. For a voltmeter, you didn't have to do that. For a voltmeter, you just kept it out here and just touch those leads wherever you needed to touch them. But for an ammeter, you have to break the circuit to let this ammeter in. But I can move it wherever I want. I can put it down here. That tells me the current in this strip. Again, ammeter's always hooked up in series with the element that you're trying to measure. So this ammeter position will let me measure the current that's flowing through the battery. But why is the voltmeter always hooked up in parallel and the ammeter always hooked up in series? We want the ammeter to be hooked up in series because we want to measure the current through a line in the circuit. We want to measure the current flowing through this resistor. So if we want to measure the current flowing through something, we need to make sure that the current flows through our ammeter, and that's how we get our reading. Because of this, people design ammeters with very little resistance. An ammeter has very little resistance. And the reason is, if you took this ammeter and it had a big resistance and you stuck it in here, you'd be changing how much current flowed through this part of the circuit. We don't want to do that. Whenever we measure something, we don't want to disturb it. So when I stick my ammeter in here, I don't want to disturb how much current was going through here. I wanted to know how much current flows without my ammeter being in there. So when I put my ammeter in there, it better have very little effect on this circuit. That's why we make this ammeter have a very small resistance. And that's also why you can't hook this ammeter up in parallel, because if you did, look at what would happen. This is why it's bad. If I took this ammeter and I hooked it up right here, and I hooked it the other side up right here, look at what the current's going to do. I've got current flowing through here. Current comes this way, goes this way, reaches this fork in the road, and it's got a choice. It can go to the left, or flow up through here and go through R3, or flow through my ammeter, but my ammeter has very little resistance. I mean small, maybe on the order of a milliohm. So all of this current that's flowing through here, all this current's going to choose to go through my ammeter. It's going to just skip all those resistors. Forget that. It just goes through the ammeter. If you've got a normal sized voltage, maybe 9 volts, 3 volts, hooked up to a milliohm, you're going to burn out your ammeter. There's usually a fuse in here because they know people are going to hook it up wrong. I've done that. And you burn out a fuse, you got to go replace the fuse, and it's a pain. So don't hook up your ammeter in parallel. What about voltmeters? Why do we hook those up in parallel? Well, a voltmeter is hooked up in parallel because we want to know the voltage across a circuit element. So on either side, voltage, remember, is defined to be the difference between electric potential at 2 points in space. It makes no sense to ask, what's the voltage through a certain point in a circuit? You can ask what current flows through that point in the circuit, but asking what the voltage is at a particular point in a circuit makes no sense. The only thing that would make sense is asking what's the voltage across 2 points in a circuit. So I can ask what's the voltage between this point and that point. That makes sense. Or I can ask what's the voltage between this point and that point. That makes sense. But asking what's the voltage at a point or through a point makes no sense. That's what current is. Current flows through a point. Voltage is across 2 points. The difference in electric potential between 2 points. That's why we hook up voltmeters in parallel. And because we hook up voltmeters in parallel, voltmeters have to have a huge resistance. Sometimes on the order of hundreds of thousands of ohms or even millions of ohms. So this can be big number of ohms. And the reason is, think about it. Again, our key idea is that we don't want to disturb the thing we're measuring. I'm measuring the voltage across this resistor. If I were to hook up a voltmeter with very little resistance, I just told you what would happen. This current that's flowing out of the battery would all try to go through this voltmeter. It would, not only would it try to mess up the voltmeter, but that's current that's not flowing through R3 anymore, and so I wouldn't get a correct reading for the voltage through R3. So we want to make sure our voltmeter has a big resistance so that, yes, I mean, technically a very small amount of current, maybe a milliamp, will flow through this voltmeter because it's got to take a reading. But we want as small amount as possible because we want to keep this current flowing through R3 the same as it was before we were measuring it, because I know V equals IR. And if I can measure this voltage across here, I want to make sure the current's the same, or I won't be getting an accurate measurement for the voltage. You could ask what would happen if we did hook up the voltmeter in series instead of parallel. Voltmeters have a huge resistance, so if I stuck that here, the voltmeter has a huge resistance. You wouldn't break it. It's just that, think about what the current's going to do. Current comes out of this battery. It's got a choice. It can go up here through R3 and the voltmeter, or through R1 and R2. I said the voltmeter has hundreds of thousands, even millions of ohms, so this current's just all going to go this way. Forget that. It's going to skip this entirely. If you hook up a voltmeter in series instead of in parallel, you just kill off any current through this portion of the circuit that the voltmeter was hooked up in. You probably won't break it, So it's not as delicate as the ammeter, but you still mess up your measurement because it wasn't designed to be used that way. So remember, voltmeters are hooked up in parallel to the circuit element that you want to determine the voltage across, but ammeters are connected in series to the circuit element that you want to measure. And if you're sitting there thinking, I'm never going to hook up my ammeter in parallel, how dumb do you think I am? Well, got to be careful, because most multimeters are both voltmeters and ammeters depending on where you set the dial. So if you're sitting there all day measuring current with your ammeter setting, everything's going well, and then you go to measure a voltage but you forget to switch the dial to volts instead of amps, you'll be hooking up an ammeter in parallel erroneously. That's what happened to me. Don't let it happen to you. Check the dial on your multimeter, make sure it's on the function that you want it to be so you don't burn out a fuse.
Don't be like him, guys. All right. So, talked about current measurement, talked about voltage measurement. We talked about, well, you listened to why the public service announcement of hooking up your voltmeter and your ammeter, right? There it is. So let's get into voltage dividers. We've already been talking about voltage dividers, right? But just as a refresher, right? Here's a common voltage divider circuit, right? I've got some supply voltage, and then I've got two resistors in series. Typically, we'll take a reading across this, volts from A to C, right? Because here's node A, here's node C, and I'll take a voltage between B and C, right? What happens typically is we want to output some voltage, which we call voltage BC, right, to some other device that we're going to power. The most common use of a voltage divider is, that I have a power supply, but I don't need that much power to run, right? So iPhone charger, your cell phone does not need the full bore of everything that is coming out of the wall. It does not. Would not. Would not charge faster. False. So what happens is, well, it goes through a voltage divider, it drops down the voltage to what it needs, right? And then there's also extra circuit protection on there so that if you leave it plugged in when it is fully charged, it doesn't just overcharge, right? Which isn't a thing, right? But anyway, right? Here's my current. My current's going to flow in this direction, right? This is just a simple circuit, right? We can also redraw this as one continuous resistor, or, and then we can figure this out, right? We would assume that there's still some voltage between here and here. That's VBC, right? But it's all VBC, right? It's all one voltage now. It's really AC, but if you use a variable resistor, you can adjust what that output voltage is, right? You can have the full potential that's coming out, or you can make it higher and reduce the voltage that's coming out, right? Okay, so that's what we can do. All right. These things can do the same thing, right? They can. But what we typically use this for is for finding a reference voltage, for scaling high voltages, for measurements, for controlling voltages, for IC chips, right? So integrated circuits, op amps, for attenuator circuits. So, right, a little bit of vocab. Attenuation is the opposite of amplification, right? So if you have an attenuator circuit, you're trying to reduce the amount of signal that you have coming out as opposed to amplifying it. Use it for balanced circuits and for filter circuits. Voltage dividers are pretty commonly used. So we're going to do this example. What I want you guys to do is work on this, right? You've got a voltage supply of 85 DC volts. Your meter input goes from 0 to 5 volts DC and requires less than 25 milliamps. You need to figure out R1 and R2 to enable the meter to measure the voltage V sub not to measure V sub S. Why would you do that? All right. You need to find R1 and R2 to find VBC, right? What's your output voltage? 0 to 5 volts DC. Right? So you're starting with 85 and you want to drop it to 5 at max. Right? And you want to figure out what your scaling factor is. Okay. So start with the first part. What are R1 and R2 that allows you to measure the voltage BC? You're measuring voltage BC. Take a minute or a few minutes. Give you guys a few minutes to work on that. Yeah. You need 0.025 here, right? If we're conducting a device. So we need to make an assumption about how much current we're going to have. Right, but it depends for the overall relationship of the entire voltage drop, right? How much current's going through. Just need to make an assumption on what your supply. Yeah, no, so
Is the 5 volt, is that how, like the range that it can read?
that's the output range.
We're trying to get DC.
Yes,
R1 and R2 are, but it would still.
correct.
Cool.
Scale factor is a function of the output.
Yep.
I kind of use that word.
Okay. Yeah, they're gonna be different depending on what assumptions you made, right? So. Mhm. Mhm.
Started with our two being 1,000.
So how much current do you have coming out there? Because you're told you need to have less than 25 milliamps. Mm.
Thank you, Isaac. Hands on it. Good. Thank you.
Mhm. 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 Thank you.
We know there's 5 millimeters or two, so it has to be in.
It does. Does. One hundo, as the kid.
Will not. It should be around our. No, I did it wrong.
Back. What is the scale? How are you scaling the voltage?
Oh, am I scaling?
Yeah, like your output compared to your input, what's the scale?
Oh, okay.
Guys, there aren't questions? No? All right. How you guys doing? All right. How you guys doing? How are you scaling your voltage?
Probably like changing the part.
So let me ask you this. Compared to your input, what scale did you use to reduce? Right, right.
Yeah, I have a project management list for this.
You guys doing that?
Is that a number?
Yeah.
Okay.
How you guys doing? How you guys?
I think.
All right. How y'all doing? Hmm?
I assume the current 25.
Okay.
Is that okay?
So if you're assuming R1 and R2 are the same, huh? Because it's gonna split when it
My
gets out.
my R1 is 3,200 and my R1 is 200.
But when you go to pull it out, right, it's gonna split based off of whatever you're hooking up to there, right? So that's
If it's a voltmeter, should it be infinite resistance? So
yeah. That's not really the intention, but yeah.
like, then what was it? It's good night.
So the intention is that your meter takes less than 25 milliamps coming out, right? So maximum 25 milliamps of current going into the,
Let's just say the answer is 24.
so can you calculate based on knowing
Yeah,
that
because
that's gonna have a high resistance, right?
yeah, 'cause then if you measure cross R2, yeah, I got the scaling factor is 18.
Okay.
So like for 80 volts,
So then.
80 times that gain
Mhm.
gives us that, and then that times 18.
Okay.
gives us 80, so no.
Sure, yeah. Does everybody have something?
There will be a lot more. That's true. Or both sides.
I don't know. I didn't know what they go off. Like,
I don't know. We'll just see what happens. See what happens. I have no idea. Right now, I basically, this semester, I was just filling in where we had holes. So if we don't have any holes in the fall, then I probably won't pick up a section, but we'll see what happens. All right, does everybody have something? You guys have something? Everybody's got something. Yeah, something? Something. Pumpkins. Everybody's got pumpkins. Yeah. Okay. Got your. All right. So let's talk about this. You were all definitively wrong, but also all definitively right at the same time. I know it's crazy. Super open-ended question, right? Because you were specifically asked to essentially just figure out what these resistances are. And you can assume that you have any and all resistors available to you because there's no statement saying that you were restricted in any way, right? And so there's a lot of different ways you can do this. And you're given a range. As long as you fall between 0 and 5 volts DC, you're probably okay, right? And as long as you don't have more than 25 milliamps, according to this prompt, then you're also okay, right? So we just watched that video. How much resistance does a voltmeter have? Infinite. infinite resistance, meaning that we're not even going to worry about calculating what this resistance is because it's meaningless. We just need to use this part of the loop. So what are we going to do? We're going to use everybody's favorite, the KVL, right? Kirchhoff's voltage law, which tells us that the sum of the voltage drops in any closed loop of our circuit will be equal to 0, right? And so in this case, we have our supply voltage minus the voltage across R1 minus the voltage across R2 is equal to 0. Or if you want to rewrite this in a little bit nicer form, we'll use some really high tech mathematics that I'm not going to explain. So do, all right. I know it's rude. All right. Well, all right, that's fine. But I can rewrite both of these, right? And we have special names for these, right? We said that VR1, right? Well, we didn't really give that one a name. We'll call it VR1 still, but we called VR2 VBC, right? I'm going to call this V out because that's what we're looking for. We're looking specifically for this value. But we can rewrite these using Ohm's law, and we can say that Vs is equal to R1 times the current through our system, which is the supply current, plus R2 times the supply current, right? These are in series. They're in series, and we know that the other thing has really high, right? It has really high resistance, so it's going to have a very small amount of current that goes through it. And so we're just going to assume that these two things have essentially equal amounts of current that go through them since they're a series circuit. Okay, great. That's great. But what's I sub s? I don't know I sub s. Well, I'm going to make an assumption about I sub s, right? And my assumption is that I sub s is twice the amount of current that I want to come out. Does that matter? No. Right? You can make whatever assumption you want, right? Because it draws a minimal amount of current on the output, right? You do definitely, well, let's put it this way. You need to ensure that you are not drawing more than 25 milliamps, right? That's what you need to ensure, right? I'm going to design this such that I am drawing 25 milliamps, okay, as my output current. And so in order to make sure that I have 25 milliamps, I'm going to say that I'm supplying double that. I could supply triple. I could supply 500 times. It doesn't really, well, maybe not 500 times. That's probably not a great example. But the point is, you make the assumption, right? It's very open-ended. So I'm assuming that IS is 0.05 amps. Oh, sorry, 0.5 amps. That's what I said. Looking at the wrong spot. 0.5 amps, half an amp. So more than double, right? So I have plenty of current. And I know what VS is because that's my 85 volt supply. So I can rewrite this as VS is equal to R1 plus R2 times IS, or that VS over IS is equal to the combined resistance, which tells me that R1 plus R2 is equal to 85 divided by 0.5, or 170. And I'm going to call this equation 1. Right. And now using that, we don't need to make another assumption. We only have one assumption that we have to make here. Because you're like, well, I can just make an assumption for R1 or R2 at this point. We don't have to, right? You don't have to, because we still have Ohm's law, right? So let's go over to the next slide. And Ohm's law is going to be able to tell me that V out is equal to my supply current times R2. I know what I want for V out. I want between 0 and 5 volts. I'm going to set it at the max range, right? So I'm going to say that V out is 5. This is 0.5 times R2. So R2 is equal to 10 ohms. All right. Go back into equation 1. R1 is equal to 170 minus R2, which, shockingly, without a calculator, was able to do that math. 160 ohms. Again, you guys, based on whatever assumptions you made, right? There's more than one way to do this problem. There's more than one correct solution, right? But this is one of them. And one of the things asked to find, so we found R1 and R2, part A done, right? Part B was to find the scaling factor. Last class, I talked a little bit about what the scaling factor was, right? So if we look at our voltage divider, sorry, wrong one, voltage divider equation, it's this, right? And what we're being asked to find with the scaling factor is how am I scaling the input voltage to get the output voltage? This value right here is my scaling factor. I have values for R2 and R1. So this is going to be 160 divided by 170. Wait, did I do that? No, sorry. 10. Like I said, 10 over 170 or 1/17, right? Which is approximately 0.06. And it's unitless, right? Because the top is in ohms and the bottom is in ohms. The ohms cancel. And so my scaling factor is 0.06. So another way of thinking about the scaling factor is what am I multiplying my output, my input voltage by to get that output voltage, right? Or you can say, right, isn't V out over VS also equal to the scaling factor? So if you do it that way, that's fine as well. In this way, I am able to hit the maximum range of my voltmeter at the maximum amount of allowable current. If you use different parameters, you would get a different answer, but this is roughly the same, right? This is roughly the same steps. Right? So here's the last thing we're going to do today. Here's what I want you guys to do. Okay. And I'm going to write it. Using a scaling factor of 4, all right, of 4, I want you to make a voltage divider. Create a voltage divider that drops from 9 volts. Okay. I have to actually build it. I want you to do the calcs, figure out what your resistors need to be when you start with 9 volts and you have a scaling factor of 4. Right? You got breadboards, you got resistors, right? And you can leave once you show me that your circuit works.
If this scaling factor is greater than 1, doesn't the voltages increase?
Yes. All right. I'm at 1/4.
Okay.
Use 1/4. My bad. There you go. You're not going to amplify the voltage. It's not going to happen. Okay, I see my comments about the second law at the beginning of class. Thank you. Quarter. Dropping by a quarter.
Voltage code, voltage divider circuit.
Yeah.
9 volts, 2.25, that's 9/4. With a 0.5 current, assuming that's what we get off the breadboard, we would need a 13.5 and a 4.5. For our one mark.
Sure. Go grab them.
So we gotta actually.
You got to actually physically build it. Yep. Yeah, give me 1 second, right there. All right, what resistance? How'd you guys get your resistor?
Thirty in series, 320.
Okay.
Yeah. 2.2.
Show me across here to ground.
We just look off.
Mhm.
The value should.
It should be that.
Go. How'd you guys do the calcs with the scaling factor equation?
Yeah, we did. So we just.
Perfect.
10 ohm.
You made an assumption and then you,
Yeah.
yeah, solid. Yep. Yeah, give me 1 second, right there.
Alright,
So,
it should be spitting out 2.25 by our calculations, and it's right at 2.28, so it's pretty close.
why is it negative?
Probably because we have this backwards. If I had to guess.
It's probably fair.
Yeah, I thought that. There you go. Look at that, now it's 2.25.
You're the leads this year. Yeah. Okay, solid. Yeah. Okay, solid. So
We built it, we're good.
let me come take a look.
This one isn't too accurate or precise. But. Why is it? Like about 2.0.
Okay, so you shunted it.
So it's a little less than it should be.
Sure.
But like if you just move this over, it's not gonna fry it.
Right.
We're not. It's still two. Double digits.
Oh. Yeah.
It's, 2.2.
Solid. What resistors? are these?
100 or 100 and 300.
Okay. Cool.
Without the front, it was showing like 1.8, 2.2.
Yeah, I know what I was doing.
Messing with the dial.
That's fine, might be off. That's really small.
Yeah, so it's 15 and we want to limit it to 500.
What resistors did you guys do?
Use 30 ohms, so never get over.
How much, so when you did this, you did how much current, 0.5 amp? Right,
I feel like I'm on.
right, yep.
Which is what was our design. And then 0.5.
13 and 4.5. Yep, all right, take it easy, guys. 13.5 plus 4.5, is 18. 4.5. You mind if I?
Yeah. Just click that.
Sorry. Square. Yeah. It's weird that it's not reading out. I'm thinking that this board is not working correctly based on the fact that this is not giving you anything for the negative side. Circuit should work based on your calcs, so. One sec, and then you get us.
These are all.
Okay, so we have 3 150 ohm resistors making a 450 ohm resistor.
So that you question here. How'd you come up with these numbers?
I chose.
You picked one and then you solved their own?
Yeah.
Perfect.
I saw that 150 was one that we had.
That's how you should. 100%. Show me. Nice, yeah, right around where it should be based on the fact that it's not exactly 9, so it should be around 2.25. There it is. Solid, good job.
Yes, sir.
Ready, let's go.
What do you got? Oh, man, you're so close. I just,
Yeah.
220. All right, so what resistors did you guys pick and why?
Yeah. We found a scaling factor between resistors. R1 has to be 3 times the value of R2. So we chose 215s in series for combined resistance of 30, and then R1 is just a 10.
Should have 10 on the bottom.
215s.
Okay,
Cool.
cool. Yeah,
It's a little messy.
should be a little, I think your power supply might be busted too anyway.
Possibly, if we- Okay, we're close. We're all good?
Yeah, more concerned that you guys actually did the calculation beforehand to, verify the resistors.
Oh, yeah.
I told you guys the first day that that's the expectation, right? So don't just start. All right, so you guys are 8.9 and 2.
Turn off.
All right, I mean, it's right around where it should be.
And then
We
always
think it's because it's
disconnect.
It's not exactly 9, so it is gonna affect your measurement.
And we had the same thing where the resistor was 3 times, well, R1 was 3 times bigger than R2. So we did.
That's what we saw.
Solve for R1.
Mhm.
And then,
If you don't want the hot one.
no matter what resistor values you choose.
Does not matter. There is reason why you would pick larger ones as opposed to, like, it's just current requirements,
Yeah.
but like for this, doesn't really matter. but good, nice.
Carol sent that email to you and me about.
I saw it come through. I haven't had a chance to
Okay.
read it yet.
Attached to is the email that.
Okay.
About her thing that was. Class.
Right.
I actually got it, so I attached it to the email that I sent her. Attached it to the email that I sent her.
Okay,
So.
cool. All right, thanks. Ken, you can take off if you're still around.
Yep, then. Right now.
Yep. Let's watch it, make a comment. Easy to track.
Dr. Have you working on the homework
Mm-hmm.
and on problem 5 point, it's like the propagation of errors into the final result.
Okay.
So we make a measurement on the radius and the height, and then we're told to discuss how each measurement contributes to the overall uncertainty, I'm sorry. Is there I don't know, there on the homework, they give like little solutions and some kind of see. I just don't know where they get that equation. I think they divide the total uncertainty by the measurement of the volume.
I think what they're doing there is just really looking at like what percentage of the total error is due to the radius, is due to the volume measurement, right? If you can think of, if you can think of a different way to discuss it, that's fine too. Or yeah.
That's great, okay.
Think about it this way as well, right? Yeah, come on. Think about it this way as well. Like, is it random? Is it systematic? What kind of error is it contributing? Like, what's the type? So, 1 second, then you guys, let's see what you got. Where's the math? Use 1s and 3s.
Yeah.
Okay, where's the, there I saw 2.238. So close. I can't believe he is. It's so close. Just need that extra 0.13, and then you can, now you're good.
We had a lot of resistors that were not the right values.
That's shocking. You pulled them out of the labeled box and they weren't correct. That's
Several attempts.
funny story. These 1 year when I taught this, people left resistors in the boxes that they get cleaned out, and somebody's OCD kicked in and they had to put them all together correctly and put them back. Like, that was something that it took this person hours to untangle. It was, yeah. What you guys got?
So we got a 120 ohm here, and then a 39 ohm, which is the what is that? If we use the 120 ohm, we'd have to have or
Okay.
40 ohm, but okay.
So you got as close as possible. Good.
So it would be about, so.
You should be. Yeah.
Yeah, so,
Nice.
Yeah.
Solid. 2.23. It's pretty good.
yeah.
Very good. Good job, guys.
Yep. Thank-
If you're interested, I built it in Simulink or Simscape on the video. And I got 2.25. Nobody cares though.